Hi, everybody. Welcome to today's online meetup, Speeding Up I/O for Machine Learning. Today we'll be featuring Apple case study using TensorFlow, NFS, DCOS, and Alluxio. My name is Amelia, and I'll be your moderator. Before I introduce you to our speakers, I have a few housekeeping items. All participants are automatically on mute throughout the session. We will be using Slack to communicate, so please take a moment to join us on the community Slack channel, which we've sent you an invite for, but you can also join via alluxio.io/Slack. However, if you're having trouble joining Slack, feel free to message me your questions instead, and you can do so via the GoToWebinar control panel located on the left or right-hand side of your screen under the tab Questions. Today's session will be split into two sessions, one presented by our special guest speaker, and then the other one by Bin Fan. Before I introduce you to our speakers, I also want to remind you that you're welcome to send me your questions anytime or post it onto the Slack channel anytime throughout the discussion and presentation. You don't have to wait till the end. Lastly, today's session is being recorded and will be available for on-demand playback. We will also email you the link to the presentation as well as the recording after today's session. So that's it on the housekeeping items. Let me introduce our speakers. I'm very pleased to welcome Bill Zhao, who is the tech lead of the deep reinforcement learning research at Apple. And also we have Bin Fan, who many of you know, founding engineer and VP of open source at Alluxio. Without further ado, I'll let Bin Fan take it from here.
Thanks, Amelia. Good morning, everyone. I'm so glad to be here to present with Bill, talking about how Alluxio can help for your machine learning workloads, and we will use Apple use case as an example to illustrate how you can combine TensorFlow, DCOS, Alluxio as a stack for very efficient machine learning. So before we start, I want to briefly talk about the history for Alluxio in case you have not, this is the first time you heard this. Alluxio is originally a research project called Tachyon back in the days in the UC Berkeley MLab, where the other projects like Spark or Mises also grew. And at that time, Tachyon was a research project led by PhD students by then, and now Alluxio CTO Haoyuan Li. The project has been open sourced around 2015 and we created a company to commit to the open source mission and also get a VC, top VC backed, including Andreessen Horowitz. As I mentioned, this is an open source community and this open source technology. We have already more than 1,000 contributors on GitHub writing code to this code repository. And on GitHub, we have more than, I think today it's more than 4,500 GitHub stars. The project is under Apache 2 license, which is very popular in the big data analytics space. And we have the Slack channel. I'm always on the Slack channel to help users understand their problems and to provide suggestions. You're welcome to always contribute to the source code. We have the GitHub link here. Alluxio's open source technology has been adopted widely across the world in the past few years. And this is a landscape you can see different companies in different sectors are using Alluxio as a technology to power their data infrastructure. And we see from financial services to retailers to analytics service or technology sectors, all kinds of different companies can see from this slides. And today we will particularly use Apple as one example to show how you can benefit the AI workloads, machine learning training jobs using Alluxio. But what is Alluxio? If this is the first time you hear Alluxio, I want to introduce Alluxio from three different technical innovations perspective. So in the high level, Alluxio provides a data abstraction to decouple the compute and storage. So if think you're in the analytics or AI stack, Alluxio is adding a new layer into this stack. So it's not a new computation framework, nor it's not a new storage engine or a new storage service. Instead, Alluxio provides a data abstraction in between the computation layer and also the storage layer. So on top of Alluxio, you can run analytics workloads like Presto, Spark, or Hadoop MapReduce, or AI workloads like TensorFlow, PyTorch. Alluxio provides different popular APIs to interface with these computation frameworks, including the HDFS compatible API, which is very popular in the big data analytics world, or the POSIX API, which is very popular in the machine learning world. And underneath, Alluxio connects to different storage. And Alluxio provides different drivers, including HDFS driver, S3 driver, NFS driver, or different drivers. So from user's perspective, it's talking to this data abstraction using their favorite APIs. But underneath, the users, they don't need to care about where data is stored, how the data is stored, which is library version, and all this very detailed and detailed setup. Alluxio can help hide this abstraction, hide all these details within the abstraction. So as mentioned, it provides a common file system abstraction. And in a big data analytics world, you can just simply change the HDFS. Originally, if it's using HDFS, you can simply change the HDFS URL to Alluxio URL to provide this data abstraction. And by hiding this detailed implementation of storage, it provides greater flexibility. For example, you can connect Alluxio with S3 or Azure or Google Cloud storage without even letting the users notice the change or the difference. And so this is basically provide a common abstraction on the file system. We also provide unification on different storage. So take this slide as an example. You can use Alluxio to provide a logical Alluxio namespace in the middle, illustrated by this blue tree, which is the logical namespace user can see from Alluxio. Underneath, it can be actually from two different Ender storage namespaces. One is from HDFS and one is from S3. By mounting these two different Ender storage into the single logical Alluxio namespace, users just they have the feeling they're dealing with only one file system, and Alluxio will handle the complexity inside. So this provides a very effective way to manage data across different storage. If you have, for example, different data storage in your platform. And also, Alluxio provides the on-demand data caching. As Alluxio started as a research project called Tachyon, it was mainly providing a in-memory off-heap data storage or data caching for RDDs in Spark in the very early days. So now Alluxio has developed many rich sets of features providing a good performance by bringing data to where the compute is. So essentially, you can allocate different storage resources to Alluxio, including memory, SSD, or hard disk, and Alluxio can help manage this storage resource as a black box to the applications. So it's a distributed caching service to the applications, and how data is migrated between tiers or retiring from the Alluxio space is totally transparent to the users and to the applications. But for data which is very frequently used, or you can specify your own data replacement policy, but based on the replacement policy, it tells the data is hot or this data is cold, and hot data will be fetched from the Ender storage to store in the Alluxio space. Even more, hotter data can be even replicated with more replicas across Alluxio space, with more replications to help speed up the performance. Or colder data can be migrated to lower tier or even expired from the Alluxio space. We provide different APIs to help users set data policies, including pinning the data in Alluxio to certain tier, or promote and demote data, and also set TTLs to data. For example, if you know some data you will only need for an hour or for a day, you can definitely set a TTL for the data so it will expire from the Alluxio space after TTL expires. Yeah, so all these are belongs to the data policies you can use with the on-demand data caching. And the key here is Alluxio bring data from a remote, can bring data from the remote storage to someplace closer to compute and enhance the performance by bridging this data locality. The last perspective is about API translation. So as I mentioned, Alluxio provides favorite or popular data APIs to different applications. And today, we see most people using the big data file system API, like HDFS API, and also the POSIX file system API for AI workloads. And we will translate the API calls underneath to different storage you choose, including S3 or HDFS or Google Cloud or some other storage you choose. And this will help users to hide the implementation details for the storage. And you only need to care about one API, which can be backed by storage with many different types. To give you some examples using Alluxio to access data using different tools. If you're running Spark, to load a RDD is very similar to how you can do this with a HDFS or S3. Just change the scheme name from HDFS to Alluxio. And it's also very similar to Presto, because Presto and the Spark are both typically are using the HDFS interface to interact with the data. And for Alluxio, because we mentioned it provides the POSIX compatible API, you can mount Alluxio the Alluxio service as a local folder into your local laptop, and in that way you can just use your familiar bash script or a command to interact with data with Alluxio. And this is actually the same way for machine learning workloads like TensorFlow or PyTorch to interact with Alluxio. We also provide a native Java API, which is very similar to Alluxio, to Java standard file system API. And within this Java API, our native Alluxio Java API, you can access the full feature of all the data policies, all the APIs Alluxio is providing. So if you are able to customize the way you are interacting with Alluxio, then this is the recommended way. In the next session, I want to talk more about using Alluxio Fuse API or a POSIX API, which is backed by Fuse. And in the high level, using this POSIX API, Alluxio can make the remote data look like a local data. So what is the Fuse-based POSIX API? Essentially, you can mount Alluxio and expose Alluxio to a local file system, including Mac OS or Linux, as a local folder, local directory. So in this local directory, applications can interact with Alluxio using standard POSIX APIs, including open, read, and write, without any code change to your client. Note that because in the back, Alluxio is implemented as a write once, read many file system. So this mounted file system to the local folder will not support all the POSIX workloads, especially for in-place updates. But you can totally write data, appending data to the keep writing data to a new file, keep appending data to a new file, and that is supported from the Alluxio semantics. So this is a diagram shows you how it works. So essentially, you can mount first in the Alluxio space, you can mount a remote or distributed storage into Alluxio namespace, as I mentioned before. And then on your local desktop or on your local laptop, you can mount this Alluxio service into the file system, and then you can interface with the deep learning or machine learning workloads frameworks, including PyTorch or TensorFlow or these kind of different frameworks. And this shows you how the Fuse interface makes the data available locally, although they are actually backed by different storage. And notice that Alluxio provides the data caching, and if you're accessing data from these different folders, actually this will be cached in Alluxio space. And if you're running even Alluxio workers locally, and you can just basically access locally cached data. And this diagram shows you some performance benchmark we did before by running a TensorFlow to train TensorFlow jobs using AlexNet, accessing data on S3. With S3 data access, and which is remote, you get a relatively low throughput in terms of images per second to train. But with Alluxio in between, and once the data is cached, and the performance is very similar to what you can get with the data already loaded locally. You can see the blue curve is the Alluxio through Alluxio Fuse, and the yellow curve shows you once everything in the entire image input data set is loaded locally. If you want to learn more details about this experiment, you can go to the link I show below. Yeah. So here I want to show a workflow to run machine learning workloads in a step-by-step way. First, you have to launch Alluxio. So this shows you how you deploy Alluxio locally by launching Alluxio instance using one single command, Alluxio start.sh with the argument local with -f. So what this is doing is to start a local Alluxio cluster, and we will start this as a whole new cluster by formatting everything, formatting the Alluxio file system. So there will be no file recognized in Alluxio after starting this. This is a whole new file system start. And then one example is you can mount a S3 bucket into Alluxio namespace. You can mount using this mount command, and this will just mount I have a public Alluxio quick start bucket on S3, and you can just also try this by mounting this bucket into your Alluxio logical namespace. And you can check out the files through Alluxio file system API command line through Alluxio FSLS, and you can see the data shows basically through the Alluxio API, the user, the group, the size, and whether it's persisted, and it shows it's persisted because the data has already been loaded into S3. And there's a number 0% here, indicating the data has not been loaded into a local Alluxio cluster space. Although we recognize the file, we know the size of the file, who creates this file, the last access time, all this kind of metadata information, but the data of this file has not been loaded into local cluster. So that's why you see the 0% here. So next step, you can mount Alluxio namespace, mount Alluxio namespace as a service into your local folder, into your local file system by running this script we provide, Alluxio Fuse mount. And by running this, the Alluxio service will be shown as a local folder called /mount/Alluxio. And now you can just also run different ways to check whether data is backed. You can either use AWS script, AWS S3 to check the data on S3, or you can use Alluxio command line to check the data in Alluxio logical namespace, or you can now even using the bash command ls to check the data. So basically the same data, you can check it in three different ways. And they all show you, they all pointing you to the same physical file on S3. With data mounted, you can run the training script like this is I'm using the image classify Python script to run this. And then after the training job's complete, you can stop Alluxio mount and also stop the Alluxio service. And I have a tutorial here below on DZone and talks about the entire process. This is a step-by-step tutorial teaching you how you can run Alluxio to turn your cloud storage or HDFS into your local file system, and to be able to run machine learning workloads like TensorFlow on top of the local data. So having talking about so much about what Alluxio is and how to use Alluxio to serve machine learning workloads. I want to actually spend a few more slides to talk about when it may provide performance benefits or provide other benefits to your workloads. So the first scenario we see is to support more frameworks across different data centers. If you have some workloads already running in your data center and already being able to talk to this the data lake, for example, HDFS in your data center, and you can add Alluxio as another. You can add Alluxio to help your workloads from a remote data center or a satellite data center, a satellite cluster, access the same data lake. So in this case, I'm showing you, for example, you have already a data center B with all the other Hadoop workloads running, and you're now launching another data center to run a different workloads, what we see typically like a Presto or some machine learning, because they require a lot of memory or GPU specialized hardware, and you can use Alluxio as the caching layer for this computation to work better instead of always going to the data lake, always going to the main Hadoop cluster. You can take advantage from data locality with the data cached in the Luxio space. So another case we see a lot is by running, for example, in the cloud. You have a single cloud, you're running the workloads on a single cloud stack. You're running Spark or you're running some other applications, but you do not want access data from S3 or your Google Cloud Storage repeatedly. And in this case, you can use Alluxio to deploy it with your computation, and this will save your time to read data repeatedly. Besides, what we found in the past is cloud storage typically is implemented as the object store has some limitation or a semantics difference compared to a traditional file system. The performance is can be variable. This is because it's remote from your storage, from your compute. And also the metadata operations are commonly reported to be expensive, especially for workloads like rename or list. This can be very different because the implementation details is implementation is different. The performance implication is also very different. For S3, we also see a lot complaint on the eventual consistency. So Alluxio provides its own metadata service and to enforce a strong consistency across files in the file system. So it can hide the eventual consistency from the applications. Another case we see also a lot is we call the zero copy bursting from hybrid clouds. If you have some data in the own data center, but you also want to leverage the application, the computation resource to run applications in the cloud, and this is what we call the hybrid cloud environment. What you can do, you can have Alluxio in this picture to be deployed with your applications in the cloud. So Alluxio can help fetch data from your data center, your HDFS data center, and cache data in the cloud. So your applications like Presto, some other applications do not need to read the data repeatedly cross-while, which can be expensive too. The last case, what we call, is the object store, big data on object store. We see a trend. A lot of HDFS use cases are in the transition to object store, which is more scalable and more friendly to small files, but also cheaper. Also, on the implication is these object stores typically can have similar semantics as what we mentioned on S3, and also because it's different from HDFS, it's no longer deeply coupled with applications. So having a layer like Alluxio to help speeding up the performance from object store can turn out to be very helpful. So this is similar to what we are showing today using the Apple use cases. I will just handle this to Bill.
Hello, thank you, Fan, for introducing this. And also thank you for Luxio inviting me to share some of our use case for this data processing needs using Alluxio within our organization. So without further ado, could you go to the next slide? So our motivation right now is that we have a lot of data we need to ingest, and then we need to process. And then once we process data need to be searchable, and then we need to run some analytics, and then also some learning on those data and create some ML model. So basically, the workflow is from ingestion all the way to the learning platform. And we were doing this for the past few years, and we saw a lot of problem when we reading the data and processing the data. So we were able to test Alluxio and some other storage needs. So we let me show you the platform diagram. Could you go to the next slide? So our platform is we're running our software inside a Docker container. So most time we might be running TensorFlow or PyTorch, and we need to copy the data out to do some processing. And the main orchestration platform you'll see in the middle right here is DCOS. This is by Mesosphere. We're a big Mesos shop within Apple. We have a lot of different clusters running Mesos. And at the same time, each of our machines are heavily loaded with a lot of memories. So we want to utilize those memories. So we copy a lot of data from our infrastructure, which you can see down there. The persistent storage block showing on the diagram is mainly our IBM HDFS storage, very similar to EMC or any other big storage. We have tons of storage in there, petabytes of data. But the bottleneck is getting that data out to the user who are actually going to use. So we have this flow. Is we're using the platform to orchestration, which container running on what server, and then we pull the data out from the persistent storage to the server. But because we're using mostly NFS, and that time is just taking a long time, I'll show you some of our pain points in the next slide. So next slide. So as you can see, our architecture is mainly TensorFlow and PyTorch or some other deep learning platform, and we're using DCOS to do the orchestration of the Docker container, and we're pulling data from the IBM HDFS storage. So every time when we do that with NFS, the data rely on pulling through the the network infrastructure. And if we're doing a single job of a single data point, that's fine. But a lot of time we might have multiple jobs reading the same data block, and that could decrease our speed dramatically. And we are not able to run a lot of this job concurrently, and our speed of completion of the job is very slow. So that's why we try the Alluxio. And basically, the Alluxio gives us this flexibility of getting the data into the memory and marking those data as hot or multiple use. And this way, we were able to run multiple jobs running the same data block. And initially, we were trying to pull this on NFS. We were running a lot of NFS server, but still, when we're running the same data block and running multiple concurrent jobs, it slows us down dramatically. And we did many tests between NFS and Alluxio, running on Alluxio fields. And you will see on the next slide what's the speed up and what's it look like. So could you go to the next slide? So this chart is self-explanatory, but I'll just go over. Basically, we're running a test, 10 gig file size. On the bottom, on the y-axis here, we have a number of concurrent jobs we're running. And then on the y-axis, we show how many, we will do random rates, and we show the speed of random rate. So as you can see, the yellow line showing the fastest possible, that's using Alluxio short circuit. And on the green line, that's just showing using regular Alluxio fields. And then the bottom blue line is NFS. So as you can see, on a single job, the speed is approximately the same between Alluxio and NFS. But once we reach the second concurrent job, that NFS is dropped, decrease significantly on the speed of read. And by the time we reach the fourth job, it just cut in half the speed. But with the Alluxio fields running on short circuit, which means just short circuit to the memory, that speed is very consistently, no matter how many jobs we throw at. If you see from 128 concurrent job or 256, it can level pretty consistently throughout the performance. And let me see. So we can go to the next slide. So the key thing is that we can run a lot of concurrent job, and then the performance does not drop using Alluxio. And the short circuit, which I think the Alluxio folks call this based on domain socket, they provide further performance improvement and very consistent performance improvement throughout number of jobs. From either you're running a single job or 256 concurrent jobs, you level out pretty consistently. And then they stay at the maximum throughput of a single job, so which is very dramatic for us. And on the next slide, I can show you some of the details that we run. If people are interested, you can take a closer look. I label them NFS 128, just mean 128 concurrent job, fields 128 concurrent job, and then fields with short circuit, Alluxio fields with short circuit. And you can see the speed that's highlighted in red. That's the throughput of the jobs. And I think that's conclude my my presentation here with the Alluxio running on fields and our use case. If anybody have any questions, please post those questions. I can answer some of them. Thank you.
Thanks, Bill. So this is the last slide for my presentation. Essentially, I'm presenting you the open source technology to unified data access as a unified data access layer for both big data and machine learning workloads. And for this particular talk, we focused a lot on the machine learning applications using the fields-based POSIX API. So this can present the data to from remote or some distributed storage or storage services, and locally and caching the large data sets from the cloud to your local, from cloud or some storage to your local computation training work. And you can definitely try this out. This is a free open source software. You can just download this from the alluxio.io/downloads. And you're also welcome to join the Alluxio community. I'm always, as mentioned, I'm always on the Slack channel. If you see any questions, feel free to talk to us. Yeah, so I think we can go to the Q&A session.
Yeah, great. So we have a couple of questions incoming already, and a reminder, you're welcome to send me the questions through the GoToWebinar control panel under the questions tab, or Slack it onto the general community channel. So our first question here is for Bin. Will there eventually be support for a Python connector for Alluxio for native client support? Fuse requires root privilege, which most users don't have.
Yeah, that's right. So I have a few comments on this question. So one is, we do have a experimental Python client actually. So based on the REST API, REST API we're providing, there's a Alluxio Python repository in the Alluxio GitHub repo providing a Python binding for this REST API. So essentially, if you're running or writing your applications, training jobs in Python, you can directly call this Python binding to access data in the Alluxio service. So yeah, that's basically that's one way to go for it. But like I can definitely understand some people may have some privilege issues to run Fuse, but that's basically a very common way to right nowadays to use a storage service as a local folder, like to make this showing up locally. Yeah, but on the other side, we also provide Docker images. Today, like in the Apple's case, in Bill's example, they're running the containerized environment, and we do provide Docker images, including the Alluxio Docker image and also Alluxio Fuse Docker image to run on your host machine to expose this to different Dockerized applications. You can also check it out from our documentation.
Great. Our next question here is for Bill. Why use the Docker container to run the ML jobs?
Thank you for the question. That's a very good question. Basically, when we're dealing with different type of machine learning or deep learning jobs, it tends to happen is a different research choose their own platform, and for varieties of reasons. So even between TensorFlow and PyTorch, because missing is the dynamic graph in PyTorch. So that's why we have to use different platforms. And then with different platform, it's much easier to load into a Docker container, which is a kind of universal container format. So this way, no matter what kind of specialized tool you need, you can put into any container you want, and we can launch the container. So that solves that problem.
Great. Our next question here is for Ben. Would it be beneficial to run an Alluxio worker in the same machine where I configure a Fuse mount?
Yeah. So essentially, if you have a worker closer to the compute in general, it will be benefiting the applications because Alluxio can just bring the data closer to the compute, and the best way is to co-locate your compute with Alluxio workers. And we have a mechanism behind to let Alluxio client embedded in the application side to tell, okay, I have a co-located worker, so let's not use network, let's not transfer data through NIC, but instead let's go through file system or domain socket, which can be much faster and also requires less resource. So that's definitely helpful for performance. On the other side, there's actually challenges in the containerized environment because the way a container is running. So essentially, we recommend run this Alluxio worker image with your application image on the same host machine, but not necessarily in the same pod, which can be actually harder to, like if you're running them in the same pod, that can be very hard to achieve. But as long as you're running the same, these are different applications with Alluxio workers, Docker images on the same host, that should be good enough. And we have, as I mentioned, we have mechanism to tell they're on the same container, and they can use certain ways to speed up the data transfer.
And our next question here didn't specify to who, but the question is why the performance drops dramatically in the case of 256 concurrent jobs from the slide. It shows the performance drops to 1 megabyte per second. Is it due to cache miss or metadata overhead?
The case for our case, we were testing this using our NFS server, and I believe because of the NFS, maybe the data we were accessing is on a single NFS server, and then we'll have 250 concurrent reads. Because those 250 concurrent reads are spread over our Mesos cluster. The Mesos might run those jobs on maybe 256 servers, but might not be. But let's say, we're running over 50 servers. So 50 servers with 10 gig connection to the network, each is trying to read that much data as quickly as possible. That can overwhelm that particular NFS server. Even we have, let's say, multiple NFS servers serving the same data, they're gonna have a lot of miss. And the test from our cluster setup between the Mesos cluster and the NFS cluster and the IBM storage, that tends to be the performance number we see. They might be more performance tuning or something for NFS server, but because of the dynamic nature of the data and the amount of data, because we have petabytes and petabytes of data, we don't know exactly which block of the data those jobs might need. So many times they have to pull in from the storage. So basically the disk.
Great. Our next question here is for Ben. Can Alluxio help machine learning frameworks such as TensorFlow run on top of object stores, and how does that work?
Oh yeah, definitely. That's basically very what we see actually very active in the community nowadays to run this, especially the TensorFlow in a Dockerized environment, in a Kubernetes environment, to access cloud-based object store. Because you're running this machine on this machines which can be remote or at least not close enough to the cloud object store storage, and this sometimes it can be very I/O intensive, causing bottlenecks in network or on the S3 and also on the cloud storage side, and also the throttling can also kicks in. So we see people are complaining this from time to time, and one solution we recommend is really to just co-locate Alluxio with the computation, or at least close enough to the computation, to training, and then to speed up the training by caching the data, caching your data sets into Alluxio. Yeah, I'm working with multiple different companies right now to further explore a lot of like best practice or performance tuning, and we keep improve the Fuse implementation. So yeah, that's definitely recommended.
Great. Question for Ben. Does Alluxio provide a CSI driver?
Good question. Yes, we provide a CSI driver from version 2.1, and you can find this out in the Alluxio code repo. I think it's called Alluxio-CSI. Yeah, this is part of the 2.1 release, one of the contribution from community.
Great. A follow-up question for Ben. Does Alluxio consume much memory?
Yeah, that's a good question. Interestingly, a lot of people have the impression that Alluxio is a memory or in-memory file system, something like that, which is true. Or actually, in the early days when Alluxio was called tackling in the research project, and it serves as the in-memory off-heap storage block management system for Spark. But later on, like as the project grows, we actually supports more different types of storage. In addition to memory, we also support like SSD or hard disk. As long as you allocate this storage resource to Alluxio, we can handle this for you. What we see in the past, here is maybe some, I will see some recommendation. In the past, what we see from the users, if you're running big data analytics workloads, putting data in memory may not be the best cost-effective way to do this. And we see from time to time having data in SSD provides a good resource efficiency and also the very high throughput already. But there is actually a caveat here. What I see in the recently is for a lot of machine learning workloads, training workloads, because it's highly concurrent, and also with the latest GPU advancements, some applications, some training jobs can really take I/O very intensively. So in that case, it really depends on your application. You can just measure this and your hardware. I would say sometimes I do see it requires memory to keep up the capacity, the consumption capacity on the machine learning workloads. Yeah, but I would say like it's case by case. Typically, SSD is good enough, and in the rare cases, we see people really require memory to serve the data.
Great. Our next question here is for Bill. Why not add more hardware to the NFS cluster?
Uh, I think that's a good question. I think we tried. We add as much as we can. Uh, However, there's some limitation on NFS. And then plus the dynamic nature of the rate of the data or accessing of the data. So it's really hard to know which block, eventually gonna get needed. So we cannot, infinitely increase our NFS server capacity. We still need some servers to actually run the computation job because that's where the action happens. So we cannot just devote all resource to that. And basically, the answer is just the dynamic nature of access of the data and then the limitation of the resource. We cannot just infinitely add NFS server.
Great. Our next question here is, could Alluxio Docker containers be run in a HashiCorp Nomad cluster as compared to Kubernetes, where we can utilize GPU resources for machine learning?
Oh, yeah, the short answer is yes. You can go to our company blog, and there is actually a recent blog contributed from an engineer in India talking about his experience running Alluxio with Nomad with Presto in the Alluxio with Presto on Nomad cluster. And I believe, yeah, Amila, can you send it to the question? Yeah, and I believe you can do similar thing in the Nomad for GPU applications.
Great. So those are all of the questions we have so far. We still have a couple of minutes here, so our speakers are happy to hang around if you have additional questions. But if not, thank you everybody for joining today, and we look forward to having you next time. And thank you, Ben and Bill.
You're also welcome to join the Slack channel. Like after this webinar, after this online meetup, you can always go back and ask us questions. I'm always there.